Hello everyone, believe it or not, the long-promised next generation of solar panels are here. A tandem perovskite solar panel with higher efficiency than silicon alone has just arrived on the market. The first batch has already been purchased by an undisclosed U.S. customer, which will soon install them in a 15-20 megawatt plant alongside traditional solar panels. This isn't just hype, this is happening, and to be clear, this video isn't a plug or sales pitch. But perovskites, whether used in hybrid setups or as fully functional solar cells, have finally materialized thanks to some big breakthroughs at Oxford PV, and that's not the only research team that's propelling perovskites into the present. So how did Oxford PV pull it off? What's the catch? And has anyone else cracked the code on perovskite durability issues? Back in April, I predicted 2024 would be the year for perovskites, and it looks like English company Oxford PV is proving me right. The company has just shipped its first commercial batch of tandem perovskite PVs, the first time these panels will be deployed anywhere in the world. This is a huge milestone, not just for perovskites but for solar tech in general. So, why is this such a big deal? Let's quickly recap what perovskites are, and how they've finally broken out of the lab and into the market. In simple terms, perovskite describes any material with the same crystal structure as calcium titanium oxide. As we've talked about on this channel before, crystalline structures are incredible at efficiently moving electrons. I spoke with Oxford PV Chief Technology Officer, Chris Case, who explained why this crystal structure is so important. I always like to remind people, salt and diamond have the same crystal structure, but boy are they different materials. Just as graphite and diamond have different things, they are the same material. The orientation of the atoms is quite unique. In the case of perovskite for solar, they're different atoms that were combined, yet they uniquely do something that makes them very good as a solar absorber. Perovskite solar cells could be a game changer compared to silicon, the current go-to material for PV. Silicon is durable, affordable, and relatively efficient, but it's bumping up against its theoretical efficiency limit of 33.7%, the Shockley quasar limit named after the physicists who discovered it. Enter tandem cells, which stack silicon and perovskites to push past that limit. Perovskites start in the high 20% range for efficiency, higher than standard silicon panels available today, and are theoretically capable of much, much more. The implications are huge, but there's a catch. While perovskites outperform silicon in almost every key category, there's one glaring weakness: durability. Historically, they've degraded quickly because they don't get along with oxygen, moisture, heat, or UV rays. Not ideal for something designed to soak up sunlight outdoors. So, how has Oxford PV engineered a tandem perovskite solar panel that can last 25 years? Oxford PV tandem perovskites, that info is still largely proprietary, which, let's be honest, shouldn't be surprising and kind of makes sense. If Oxford PV perovskite solar cells last the claimed 25 years, they're sitting on a gold mine, sun mine anyway. It's no surprise they're not eager to share their secret formula. But don't worry, the cell's performance has been independently verified by Germany's Fraunhofer ISE, a trusted name in PV research. Case also gave me the broad strokes of the Oxford PV team's approach to tackling perovskite durability. So our goal has been to reduce the degradation or sort of improve the performance and reliability of the device. So the combined device meets that same 25-year performance expectation. We've spent certainly the bulk of our R&D on perfecting and improving reliability and reducing degradation. And the approach was not mysterious because we found that some of our devices 8 years ago lasted tens of thousands of hours under high-stress conditions, but not all of the devices. So that told us something important. When you have a complicated problem, which is multi-components, multi-chemicals, and multiple layers of materials, and things from the raw chemicals all the way through the device, and all the way through to the packaged device, it's a lot of stuff, ripe for machine learning approaches. So we identify the key sort of degradation and defects at each of the places. We care about the key ones, so we can come up with a product that's good enough for the market, and that's what we've done. So we do have things that we do to control stuff at the interfaces and to passivate those grain boundaries, and of course, to make the package very effectively sealed against the environment. Again, to be clear, Oxford PV isn't shipping pure perovskite cells. It's shipping perovskite tandem cells. If you're going to beat the Shockley quasar limit, like I mentioned a while ago, why settle for one material when you can combine two? Tandem cells are exactly what they sound like, two types of cells working together. In tandem, it's kind of like the buddy cop movie of the solar world. Silicon is the grizzled vet who's too old for this stuff, while perovskite is the hotshot, smartass rookie who also happens to be a lot more fragile. In Oxford PV case, that means a trusty silicon base topped with a perovskite film, all sealed up to protect against the elements. But there's more to it than that. So back to why there's more to these new perovskite solar panels. Solar panels can absorb light from across the visible spectrum, as well as UV and infrared. Silicon, however, trends toward weaker red light at the lower end of the spectrum. Tandem cells solve this by tuning each layer to absorb different parts of the spectrum. This is one of perovskite's superpowers. It can be tuned to target specific wavelengths. Typically, perovskites are optimized for blue light, leaving the less energetic red light for silicon. This allows tandem cells to harvest more sunlight in the same amount of space. The panels Oxford PV just shipped reportedly have a 24.5% module efficiency. While that's not breaking the Shockley quasar limit, it's still a solid jump over the 15-22% range of standard silicon tech. Oxford PV has noted how quickly this tech has advanced, and there's still plenty of room for perovskites to improve. In fact, the company has stated that it thinks it can hit 30% efficiency by 2030. And again, in this sort of multi-junction form, combining perovskite and silicon, but the theoretical limit for that, 43%. We have a whole bunch of future headroom, so that's why our roadmap takes this product, well beyond 30% as a module. In fact, we tell people it's 27% in 2027, it's 30% 2030, and silicon, no matter what you do to it, it can't do that. That's exciting, but let's not get ahead of ourselves. Where are these cells coming from, and who is Oxford PV selling them to? Utility Perovskite's Oxford PV has opened a factory in Germany, which has just started supplying the first commercial tandem cell solar panels. We've touched on this in previous videos, but for now, the purchaser remains unnamed. Oxford PV has revealed that its panels were bought by a US-based utility company and are being installed alongside conventional silicon units at a new grid-connected solar farm. That doesn't narrow it down much, but it's a good sign that a US utility is confident enough to invest real money in this technology. These 72 cell panels can produce up to 20% more energy than standard silicon panels. Designed for utility scale installations, they can reduce the levelized cost of electricity (LCO) and make the most efficient use of land by generating more electricity from the same footprint. As Case explained to me, space constraints aren't just a residential problem. Higher efficiency means you can put more power into the same area. As it turns out, it's not just homes and commercial buildings that are constrained in space, it's the utilities. There just isn't a lot of available land close to the grid connections where you can put out these 100 megawatt 100 megawatt utility installations. This project will be the first major test for perovskites at this scale, and it's not just for efficiency, but for durability and longevity too. It's Oxford PV chance to prove that perovskites really can last 20 plus years outside the lab. So far, the company seems ready for the challenge. Beyond durability and efficiency improvements, its design brings other advantages. The technology is highly resource efficient, adding just 0.5% by weight of perovskite material to a conventional silicon PV cell can enable a solar module to produce 20%, 50% more power over its entire life. This increased output also helps offset the carbon footprint of solar cell production. Looking ahead, Oxford PV plans to allocate much of its production to utility customers, but also intends to supply specialty products and pilot residential applications. This strategy broadens their portfolio, showcasing diverse use cases while scaling production toward gigawatt levels. LONGi Oxford PV isn't the only company generating buzz in perovskite solar cells. Chinese company LONGi, I think that's how you say it, is also making huge strides. Earlier this year, LONGi set a new record with a tandem perovskite cell that achieved an incredible conversion efficiency of 34.6%, confirmed by the European solar test installation ESTI. This broke the company's previous record of 33.9%, and believe it or not, it's the 16th time LONGi has smashed a solar cell efficiency record since April 2021. How did they do it? LONGi's approach is all about small, steady improvements. The company calls it scientific root cause analysis plus engineering lean optimization. Really quick and easy to say. In simpler terms, the team focuses on refining many little details instead of relying on one big breakthrough. Now that I mention it, that's actually pretty similar to what Oxford PV is doing that Chris talked to me about. Specifically, LONGi has shared a few key tweaks it's made, improving how it deposits the electron transport layer, using special materials to reduce defects, and fine-tuning the interfaces between layers. These technical upgrades might sound complex, but they all contribute to making their solar cells more efficient and reliable. What's exciting is that LONGi built these improvements on its own commercial CZ silicon wafers, which are thin slices of silicon made with a popular production method. Because LONGi already makes these wafers in large quantities, the company can add perovskite layers without having to build brand new factories. This gives it a major advantage in scaling up production without driving up costs. But here's something to keep in mind. Individual solar cells often lose efficiency when they're connected together to form a panel. While LONGi holds the record for the most efficient single cell, Oxford PV still stands with the most efficient 60-cell module, which is the type you'd see on rooftops or in solar farms. LONGi has developed a commercial prototype panel with 31% efficiency, but it hasn't announced when it'll start mass production. For now, it's a wait-and-see situation. Meanwhile, researchers at Rice University in Houston have found a way to make perovskite solar cells more stable by improving a type of perovskite called formamidinium lead iodide, or FLI for short. Think of FLI as the main ingredient in these advanced solar cells. To make FLI more durable, the research team used a clever trick. They started with stable 2D perovskites as a foundation. It's like building a house on a rock, solid base to keep it from collapsing. By adding these 2D crystals to the FLI solution, they created a stable base layer that helped the 3D perovskite layer on top perform better and last longer. And the results? Pretty amazing. Solar cells made with this method lasted 10 times longer in air than regular ones, staying intact for 20 days compared to just 2. They also achieved an impressive energy efficiency of 1% for a 0.5 cm area and retained 97% of that efficiency after 0 hours at 85 degrees C under maximum power tracking, another perk. These cells can be made at much lower temperatures, only 100 degrees C2, 112 degrees F instead of the usual 150 degrees C3, 102 degrees F. Lower temperatures save energy and cut costs. Plus, since the perovskite material starts as a liquid, it can be painted onto surfaces like glass, heated, and then boom, you've got a solar cell. This low-temperature process might even allow solar panels to be made on flexible materials like plastic, opening the door to cheaper, lightweight, and bendable solar panels. Of course, this is still early days, and a few weeks of durability isn't enough to compete with Oxford PV proprietary methods, which are already in production. But it's an exciting step toward making durable, efficient perovskites at scale with less energy. That's exactly the kind of breakthrough that could make perovskites a bigger part of our world. Conclusion: so, where do perovskites sit on the technological readiness level TRL chart? After years of hovering somewhere in the middle, I think we can finally place them near the top. They're on the market and likely to be available to consumers soon. Perovskites are here, but it's worth reflecting on the journey that got them to this point. Reaching this level took years of R&D from Oxford PV and others, and the work is far from over. As Oxford PV scales up production and tandem cells become more widely available, it feels like the solar industry is stepping into a new era. To speed up this transition, Oxford PV is exploring licensing its technology to third parties. This approach could help the company scale faster than going at it alone. I'll leave the final word to Chris Case. We can't do it by ourselves, so we're just absolutely open to, doing partnerships and collaborations and joint ventures with anybody. We want to see deployment like you did, as you've said in some of your videos, the all-electric world. But what do you think? Are you excited by the thought of finally getting your hands on perovskite solar panels? Jump into the comments and let me know, and be sure to listen to my follow-up podcast still, where we'll keep this conversation going. Thanks, as always, to my patrons for your continued support. Keep your mind open, stay curious, and I'll see you in the next one.